In this video, I aim to go over a problem involving student loan optimization, which is an example of debt contracts. We're going to use the Lagrangian to work out the optimal repayment contracts offered either by a government or by a private loan firm. So to start with, we need a couple of definitions. So, the notation does vary, but these are my basic definitions for debt contracts. So the contract is a function of earnings. So if the earnings are given by the variable y, the contract is r of y. The investment is I, so that's the money which the student wants to borrow, the amount of money the student wants to borrow, or the amount which the government or the company is willing to give. The realized return is Y, so that is what the student will be earning. And then repayment is R of Y, so obviously whatever the initial contract was, the student's going to have to pay that back. And these consumption functions are utility functions. So UL is the utility function for the lender. So the lender, if you think about the money the lender's going to get back, they're going to get back R of Y. Well, they presume R of Y. That's the money that was loaned out at the start. The student's going to pay that back, minus that initial investment that they need to give out. And the utility is going to be a function of what is paid back, R of Y, which obviously it could well be greater than the initial investment because obviously there's interest, various other factors. And then UE is the entrepreneur, or in this case, the person seeking the loan, in this case, the student, their utility function. Think about the money they're going to get back. Well, they're going to have their income, Y, but then you need to take away from that the money that they have to pay back. So obviously, if you look at a student loan, typically, depending on your earnings, you'll pay back different amounts. So if you earn more money, generally the government will ask you to pay back more every year, and that's basically what we have here. I wouldn't get too hung up on these. Once we start using them, it'll make a bit more sense, but this is my general notation. The expectation of a function of a continuous random variable. Again, nothing to get too hung up on because you can always Google a definition. But basically, what this is if you have a function of a random variable, so random variable is just something that can take different values randomly. So, the amount that someone earns, that could be considered a random variable in some sense. The expectation is just like the average amount that you would expect. So it looks really fancy, but basically it's the integral. Don't worry about these limits. The reason these are infinities is because it's taking limits over all the possible values that you can put in. And it's basically g of x, f of x, dx. So what that means is the actual function times by, well, you could call it the support function or the PDF, the probability distribution function. Or the probability density function, sorry. But it'll all make a bit more sense because in the examples that follow, it's very clear what the PDF is and it's very clear what G is. Finally, all the last bit is Leibniz's rule. This just basically tells me that if I differentiate outside of an integral, generally I can bring that integral inside the integral sign, differentiate what I have inside the integral, and then do the integral. Basically, I can swap derivative and integral. It makes things a bit easier. There are a lot of conditions behind that, a lot of maths behind it, but right now that's all we need. So without further ado, if we just review that, scan it, and now we'll make a start with a question. So the cost of education is I equals 0.5. So the investment you would have to put in is 0.5. Obviously, it's been scaled in some way to make the numbers easier. A student's return from education is his or her earnings Y, which are not known before the student starts education. It's commonly known that after education, student earnings take values from the uniform distribution with support 1, 2. So when it says support there, it basically means that we're going from 1 to 2, and then it's going to be some value. So, the x values are going to be between 1 and 2, and the y value is going to be some constant, but I wouldn't worry too much about that. The government offers students, essentially it's going to be, 1, 2, and then it will take some fixed value like that. So it looks something like that. The government offers student loans of I equals 0.5. So basically they offer the exact amount that we need. The government can observe earnings and therefore can condition student loan repayments R of Y on student earnings Y after education. Student preferences are given by the utility function U of X. So this is basically our UE of X from earlier on. But again, I wouldn't get too hung up on it. That's essentially UE of X. Where X is the net after repayment income. Now that's actually a really important point. That basically means we don't put Y in. We're going to have to put in Y take away R of Y because it's the money they have after they pay back their allocated amount every month. So let's make a start with the first part of this question. So find the optimal student loan repayment contract R of Y that maximizes students' expected utility and balances the government's budget and expectation. So this is basically an optimization problem. So to do an optimization problem, we obviously need some function or something that we want to maximize or minimize. And we need a constraint. We need something else about the situation that gives me a little bit more info. So to do this, first of all, I need the function that I want to maximize. Well, I want to maximize the student's expected utility. Now, if we look back at the definition of expectation, it was this whole integral f of x or integral g of x, f of x dx. It was basically the function times by the probability density function, which in this case is just this uniform distribution, which I'm going to call f of y. And then you integrate it over the whole domain. And we know that it only takes values between 1 and 2, not between 1 and, it only takes values, sorry. It only takes inputs from between 1 and 2. So we know it's going to go from 1 to 2. So we need to work out the expectation of the utility function for the student. But of course, again, it's not the net. First of all, we need to have the net income. So let me just take this a bit more slowly than how they do the solutions. I want to make sure it's all clear. So first of all, net income for the student is going to be Y. Now that is if we look at, that's the earnings, right? So that's the money they just earn after tax and everything. That's their earnings. Or maybe it's done before tax, not sure. But it's basically what they have from their paycheck. And then we have to remove from that the money that they're going to have to pay back. But that's just going to be take away R of Y. The reason it's R of Y is because it depends on how much that student's earning. If the student ends up, becoming a quant or banker and makes hundreds of thousands, they're going to pay back more every month than someone who, goes into a different profession. So the net income is going to be Y minus R of Y. So we actually want the expectation of the utility. Now, I'm not going to call it UE of X. I'm just going to do what they've done in the question and call it U of X. So expectation of U of Y minus R of Y. We want to maximize that across R of Y. We want to find the R of Y that maximizes this, subject to a condition, which I'll go through in a second. So first of all, let's just get the integral down. So I want to maximize over R of Y, the integral. This is my expectation now, from 1 to 2 of, the function I want to the function I want to maximize the function I want to find the expectation of is U of Y minus R of Y. The probability distribution function I'm just going to call f of y. That is just our uniform distribution, which actually works out very easily here. D of dy subject to, and to find what it's subject to, I look in the question, and it is subject to the fact that the government offers student loans of I is 0.5. So the government's going to give out 0.5 in terms of the scaled amount. and it has to balance the government's budget. Now, for it to balance the government's budget, what the expected value that the government gets back, which is just going to be given by integral 1 to 2 r of y f of y, again, expectation definition, this needs to be a half, because then the balance will be, the budget will be, balanced exactly, and they can expect to get back what they've given out. So this is my problem. I've got the thing that I want to maximize, this here, and I've got my constraint. So now I just need to remember my Lagrangian definition. So the Lagrangian is going to basically be the thing that I want to maximize plus lambda, the parameter, times the constraint function, or the side constraint. Now the constraint function is basically what I've underlined here, but we take the half over so we get 0. Okay, we always want to get 0 in our constraint function. So Lagrangian is going to be integral 1 to 2 of u y minus r of y f of y dy, and I'm going to, well, I'll just carry on with it for a minute, plus lambda integral 1 to 2 r of y f of y dy minus 1 half. Okay, and I've just basically taken the half over, taken it away from both sides so we get 0, and then I've put it in with lambda. And the idea is we want to maximize this using the first order condition. So basically we differentiate it with respect to r of y, we set that equal to 0, we find out what r of y, we find out what lambda is, and then we find out what r of y is. So remembering from the question that u of x was root x. So basically I can just say that I've really got integral 1 to 2 of the square root of y minus r of y, f of y, dy, and then plus lambda times all of this here. Now f of y is uniform distribution. Now the uniform distribution, if we remember this, the uniform distribution will integrate to 1 over 1 to 2. Okay, so basically the reason for that is, if I just draw it here, it's because the expectation of the uniform distribution is going to be 1. Basically, it's 1 to 2. And with a uniform distribution, it can't take any values outside of that domain 1 to 2, the way it's defined here. So that means that if I integrate it, or I get the area under it, it's got to be 1. It's got to be 1 because it can't take any values outside of that domain. So in fact, we can just call the f of y in the question 1. So I can basically write that as 1. And we can do that for both of the functions here. So we have that, which is a little bit nicer to deal with. And what we could do then, now this is what I have basically tended to do. So we could leave it all as, yeah, what I tend to do now, I would get those integrals, I would get the integrands under the same integral. So what that basically means is when I can see integral 1 to 2, integral 1 to 2, I'm just going to put this lambda inside here. I'm going to take that a bit more slowly. Sorry about that, Ryan. Take that a little more slowly. So what I'm going to do is expand this bracket first. So I have integral 1 to 2 root y minus r of y dy plus integral. I can take this lambda inside that integral, lambda r of y dy. And then I've got lambda, I'm just expanding the bracket, lambda times the first, lambda times the second, lambda times minus a half is just minus a half. You might prefer to use decimals, so I'll call that minus 0.5 lambda. And then, again, what we want to do is we want to, first of all, get the integrals together. So I'm just going to say I've got integral 1 to 2 of, and I can, because I'm integrating over the same range, or the same domain, I can bring these terms under the integral signs together. So I have root y minus r of y plus lambda r of y dy, and then it's all take away a half lambda outside the integral. And the reason I've done that is because I want to make it as easy as possible when I use my first order condition. Okay, so we basically want r of y such that dl by dr is 0. That is our first order condition. That is how we find the maximum r of y. So to do that, I'm going to use the Leibniz's rule, which we looked at the start. I'm going to remember that if I differentiate both sides, that I can bring the derivative underneath the integral. Okay, so I've got d by dr of the integral is just going to be the integral, and I can bring the d by dr underneath that integral sign. Okay, so let's do that. I'm just going to rub that out. So dl by dr is 0 implies that the integral from 1 to 2 of d by dr of everything inside here is going to be 0. So I'll just write it out a little bit more, in a bit more of a friendly way. I'll just write I've got y minus r of y to the power of a half plus lambda r of y dy, and then I've got the minus 0. Well, I actually haven't got this anymore, because if I differentiate a constant, I'm going to get 0. So differentiate this half lambda, it goes. So basically this is all going to be 0. So what I'm going to do now is just remember that, well, I'm integrating from 1 to 2. So I'm integrating over a positive domain. The square root, as far as we're concerned, is always at least 0. So this term is bigger than or equal to 0. And lambda r of y, well, r of y is just the function for the debt contract. It's going to spit out a numerical value, which is positive, so I can assume that's bigger than or equal to 0. So I'm basically integrating something which is bigger than or equal to 0, so it's going to be something like that, over a positive domain. So that means the integral, or the area underneath it, must be non-negative. So the only way that this whole thing can be 0 is if, in fact, the entire function, the entire integrand inside is 0. Okay, always 0. So it's, this bit it's not necessarily big equal to 0, but that's the point. The point is the whole integrand's got to be 0. So I can just basically say this bit inside the integral sign is 0. Okay, after obviously we've done the differentiation. So that means that d by dr of, so I'm writing there, y minus r of y half plus lambda r of y. I don't know why I'm calling it r of y. I can just call it r really. That's got to be 0. So all we need to do now is do the differentiation. So remember, in the chain rule, we differentiate inside the brackets here with respect to r. Well, if I differentiate minus x, I get minus 1. Differentiate minus r with respect to r, I get minus 1. So I have minus 1. Y will go to 0 when I differentiate with respect to r because they're different letters. Done the inner function, now we just bring the power down, take away 1 from the power. So I have minus 1 times a half times y minus r of y to the minus half. Lambda r of y, differentiate that with respect to r. Well, what happens if I differentiate r with respect to itself? I get 1, so I just have plus lambda. And this is all 0. Right, so now we can just simplify things. So I have minus y minus r of y to the minus half over 2 plus lambda is equal to 0. So what I'm going to do is take this minus y minus r to the minus half of the 2. I'm going to take all of that over to the right-hand side. I'm going to add it to both sides because that will cancel it on the left. So I'm left with lambda is equal to y minus r to the minus half over 2. So I'm going to take things one step at a time. I'm going to multiply both sides by 2. So I end up with y minus r of y to the minus half is equal to 2 lambda. Now, if we remember from a previous video that when I have a minus power, it means reciprocal, 1 over, and I have a power of a half, which means square root. So the left-hand side is 1 over the square root of y minus r of y, and that still equals 2 lambda. Right, what I'm going to do now is bring this root y minus r of y up to the right. I'm going to multiply both sides by that bottom of the fraction to give me 1 is equal to 2 lambda root y minus r of y. Then I'm going to bring the 2 lambda back down, because again, my aim here is to get r of y on its own. So I'm going to say I've got root y minus r of y is equal to 1 over 2 lambda. Then I'm going to square both sides to get rid of this square root. So I have y minus r of y is equal to, well, if I square 1 over 2 lambda, I just get 1 over 2 lambda times 1 over 2 lambda, which is just 1 times 1, 1, over 2 lambda times 2 lambda, 4 lambda squared. So I have y minus r of y, or just r, is equal to 1 over 4 lambda squared. And I can just add r of y to both sides and then subtract minus 1 over 4 lambda squared from both sides, and I get r of y equal to y minus 1 over 4 lambda squared. Now we're not actually finished. We need to put this into the side constraint, because I don't want this lambda here. I just want my contract to depend upon y. Just to, I basically want this. I want the government contract, the government debt contract, to depend entirely upon the student's earnings. This is how we do student debt, at least in the UK. Make some space. So we need to remember the side constraint, and that was just that the integral of basically the expected value, the expected return for the government would be 1/2 in terms of this scale that we've used. So I need to do. I need integral 1 to 2 r of y f of y dy is equal to 1/2. But of course, because it's a uniform distribution, that f of y under the integral, I can just basically say it's 1, okay, because it's going to be integrated over the whole domain. It's a uniform distribution, it's just going to be 1. So I just want integral 1 to 2 r of y. I want that to be 1/2, or 0.5. And to find what lambda is, I just substitute this into the integral below. Sub into the constraint. So I actually have integral from 1 to 2 of y minus 1 over 4 lambda squared dy is equal to 0.5. So, it's fairly simple. We're integrating with respect to y. I'm going to get the integral of y on its own. Well, y on its own is y to the power of 1. When we integrate, we add 1 to the power, divide by the new power. So I actually have y squared over 2. Now, this bit is a constant. If I integrate a constant, I just multiply the variable by it. So I just have minus 1 over 4 lambda squared all times y, which is just minus y over 4 lambda squared. We're going from 1 to 2, and that is going to be 0.5. And the aim now is to get lambda, or really to get 1 over 4 lambda squared. That's the easiest thing to do. So I'm going to put my limits in. My upper limit for the integral is 2, so I have 2 squared over 2. I'm just subbing in 2 for y. This is how we do definite integrals. Take away 2 over 4 lambda squared. So that's what happens when I put 2 in. Then we take away what happens when we put 1 in, the lower integral, the lower limit, sorry. 1 squared over 2, take away 1 over 4 lambda squared. That's 0.5. We simplify. 2 squared over 2 is just 2. So I have 2, take away 2 over 4 lambda squared. I can cancel the 2 and the 4. So I have 1 over 2 lambda squared. Take away 1 over 2, because 1 squared is just 1. Take away now, take away now, So minus times a minus is a plus. I'm just expanding my bracket. Minus times a minus is a plus. Plus 1 over 4 lambda squared is equal to a half, 0.5. And again, the aim of the game is to get lambda squared. So there's different strategies we could use. I think probably the easiest thing would be to get a common denominator. So on the left-hand side, I'm going to get a common denominator of 4 lambda squared. So 2, to get 4 lambda squared, I would have to times 2 by 2. No, sorry, basically I've got 2 over 1 right now. I've times the bottom by 4 lambda squared, so I have 8 lambda squared. 2 lambda squared I've times by 2, so I take away 2. 1 half we have times by 2 lambda squared, so I take away 2 lambda squared. And then 1 over 4 lambda squared just stays the same. Now, if we look at the top of this fraction, we're going to have 6 lambda squared minus 1. All of that is over 4 lambda squared, and that is 0.5. So what I could do now is multiply both sides by 4 lambda squared. So I have 6 lambda squared minus 1 is equal to 0.5 times 4 lambda squared. 0.5 times 4 is 2, so I have 2 lambda squared. So I end up with 6 lambda squared, take away 1 is 2 lambda squared. Now I'm going to try and get 1 over, well, let's see what happens. So what I can do is subtract 2 lambda squared from both sides. So I have 4 lambda squared minus 1 is 0. And then I can take the minus 1 over. So I've got 4 lambda squared is 1. And then that basically means that 1 over 4 lambda squared is also 1. And because 1 over 4 lambda squared is 1, we can substitute that back into the constraint. We can see that this part, the 1 over 4 lambda squared, that is just going to be 1. So that means r of y is just y minus 1. So that is the debt contract, which maximizes the return, well, the expected utility for the student. So it basically means the student has the most money left after they've paid back the loan every month, that portion of the loan every month or whatever. But also the government's budget is balanced, so they actually get the money back that they've put in with any interest. So the point is, it actually so it balances the government's budget. They get back in what they get back in what they've put out. They don't actually get the interest, but it also means the highest utility for the student. So this is quite a good problem in terms of real life. So let's have a look at part B. So as long as we're okay, let me just do a quick overview of what we've done. We wanted to maximize expected utility for the student subject to the expected return for the government being a half, which balances the budget because they've given away a half at the start. We put the Lagrangian in. We want to find the debt contract R, which maximizes the Lagrangian. So we did dl by dr. We just basically differentiated with respect to R, put that equal to 0. Did the little trick where if we have an integral, which is 0, between two positive limits, we can usually assume that the thing underneath the integral sign, so in this case, all of this, all of that is itself 0. So we did that. We did the differentiation, remembering, we can take it under the integral sign by Leibniz's rule. Did the differentiation, rearranged to get r on its own. So we rearranged to get r, which was y minus 1 over 4 lambda squared. We then substituted that into the side constraint, integral 1 to 2 of r of y dy is 0.5. Again, we can ignore the f of y because we can just say that it's 1. So we put that back in, we did the integration, we rearranged that to get 1 over 4 lambda squared, which we could then put back into the r function that we worked out to get y minus 1. It's not easy, but hopefully the steps sort of make sense. So for part B, we basically want to compare two different loan contracts now, or two different debt contracts. So suppose that a student can borrow IS 0.5 from his parents to pay for the education, and after education repay 0.5 out of his earnings. Which option would the student prefer, the government loan or the parents' loan? So we need to compare two different loans now, or two different debt contracts. So the expected utility from part A, so we actually need to have values now. So first of all, we want the expected utility from part A. So they've actually told us to do that. And the well, the government contract from A, R of Y, was just, so the government contract from A, sorry, my tablet just came unstuck. Let me just get my tablet working again. There we go, sorry. So there we go, sorry. So the expected utility from part A was R of Y is equal to y, I think it was y minus 1, wasn't it? It was just y minus 1. Yeah. Yeah, y minus 1. So R of y is y minus 1. This is from part A, the government contract. So we want to actually work out what the expected utility for the student will actually be, according to this. So we want expected utility. So I'm just going to use U for utility, the same as they have. Expected utility of y. Or the expected utility for the contract, actually. So yeah, the expected utility for the contract, so that's going to be U of y minus R of y. So the expected utility for the student, sorry. Again, it's y minus R of y because it's their earnings take away the money they pay back in the loan contract or the debt contract. So we want to work this out. Well, this is going to be the integral from 1 to 2, because again, it's over the domain 1 to 2. U is a square root. They told us that. Now we know now R of y is just y minus 1, so I can substitute y minus 1 in for R of y. F of y is a uniform distribution, so when we have a uniform distribution as a support, we can generally just cancel it to 1 when we're integrating for the expectation. So we just have this dy. Let's calculate this. So this is going to be the integral from 1 to 2 of the square root of y, take away y, and then minus times minus 1 is plus 1 dy. So we get the integral from 1 to 2 of y minus y is 0. Square root of 1 is just 1 dy. So we just have the integral of 1 from 1 to 2. And that's just going to be 1, because that's basically going to be y from 1 to 2, which is just 2 take away 1. I'm just subbing in 2 and 1. We get 1. So that's 1. So the expected utility, for the student, under the government contract, under the government student loan scheme or whatever it is 1. Now, what this means is if under the parents' loan that they've offered, he gets something more than 1, then he'll prefer to take the parents' option. If he gets a utility which is or expected utility less than 1, the government option is better. It's not easy. So we need to know exactly what the utility function. Well, we know the utility. We need to know what the expected utility is going to be if he borrows from parents. Well, the thing is, look at what the parents have done. They've basically said he borrows 0.5 and then he pays 0.5 out of his earnings outright. Okay, so what that means is the expectation or the actual income for the student, so after his earnings, is going to be y take away 0.5. It's not take away r of y, it's just take away 0.5 because he pays that back straight away from his earnings. So basically all we need to do is do the expectation of the utility of y minus 0.5. So that's going to be the integral from 1 to 2 of the square root of y minus 0.5. And again, we have the same reasoning. We can just do dy straight away because it's still over a uniform distribution, because his earnings are still taking values from between 1 and 2 uniformly. So we basically have to do this integral. So the integral from 1 to 2 y root y minus 0.5. And in all honesty, again, I will do this algebraically, but I'll just show you. If you have a class, actually no, this calculator doesn't do it, but on my laptop it does. There's usually an integration button. So if you have one of those if you have a modern classworks calculator, you can integrate it on there. So I wouldn't worry about these steps too much, but I'll integrate it on the screen. So I'm going to let z, I'm going to do a bit of integration by substitution. I'm going to let z be y minus 0.5 so that I have the integral from, and again, if these steps don't make sense, just remember you can go on Wolfram Alpha or you can get a classworks calculator and you can do this instantly. So y minus 0.5 is going to be just 1 minus 0.5 at the bottom end, 0.5 to 1.5 square root of z, or z to the power of a half. Because it's linear, dz is the same as dy, so I just have dz. The integral of z to the half is z to the 3 over 2, 2/3 times that. And we're going from 0.5 to 1.5. So we have 2/3 times 1.5 to the 1.5, or the 3 over 2. Take away 0.5 to the 3 over 2, or to the 1.5. We put that into our calculator. So I'm just going to put it in straight away. So 2/3 times 1.5 to the 1.5, take away 0.5 to the 1.5. And that gives me 0.989 to 3 decimal places. So under the government scheme, he can have an expected utility of 1, but under the parent, taking the loan from the parent, it's only 0.989. So in fact, it's preferable for the student to take the government option, and it's to do, I would say, with risk sharing. So the idea is that the government contract is y minus 1. So it basically means it's their earnings, take away this unit of 1, whereas with the parents, it's going to be y minus 0.5. So it basically means that he has to pay he has to pay outright 0.5, whereas with the government option, I think it's shared out more evenly. But the point is, the expectation of utility is higher under the government scheme, so that's what he prefers. So I would say, therefore, the student prefers government contract or the government loan we would say, I don't know, higher expectation, higher expected utility for the students. Okay, so the last bit of the question, we're pretty much doing something. We're doing a very similar thing to part A, just with this time with a company. So now suppose that student loans are administered by a private for-profit company. The company can also observe students' earnings, find the student loan contract ROI that maximizes the company's profit. So this time we want to maximize what the company gets, right? If it is known that a student takes a loan only if his or her expected utility after education is at least due is 0.75. So basically it's saying that they're only going to give out these loans to people that are likely to pay them back. So we can avoid subprime mortgage issues and everything. Although this isn't to do with mortgages. So we want to maximize. Let's see. We want to maximize the expected utility for the company. So the company is going. First of all, let's look at the net profit for the company. Okay, because the net profit for the company is going to take the form R of Y, because that's the money they take in the contract, but then take away what they need to pay out at the start. Now, what they are paying out at the start is student loans, the company. Now, I presume, let me find the actual original question, because I think it's still going to be 0.5, I presume, because it says, yeah, the student loans cost 0.5. So it's just going to be the money they get back, with the interest and everything, take away what they give out initially, take away 0.5. That's the net profit. So we basically want to maximize the expected utility of that. So we want to basically, actually, no, we just want to maximize this. We want to maximize that. So I want to say, I want to maximize 1 to 2 R of Y dy. So that's basically the expected value that that's the expected utility. Again, I don't need the f of y, because if I integrate the uniform distribution from 1 to 2, I'm just going to get 1 anyway, so we can leave that out. So I want to basically work out the expected value of the contract that they get back, and then I can take away a half. It doesn't matter if I put that inside or out of the integral. I'm just going to leave it outside. The reason I left it outside is makes it a little bit easier to work with. So I want to maximize this. And just to I'll actually explain. The reason we can keep taking outside is because if I put it inside, if I did this, right? If you integrate a constant between 1 and 2, you're just going to get the value again. It's not actually going to change the value. So that's why you can put it outside. Because 2 take away 1 is 1. So I can just leave it outside. So I want to maximize this. And the constraint is going to be that the utility for the student is at least 0.7, or the expected utility is at least 0.75 for the student. So that's going to be expected utility for the student. And again, the money that the student has, or the income the student's going to have, is Y. So that's their earnings. Take away what they have to pay back, R of Y. That needs to be at least 0.75. But I can write that again in terms of an integral using our definition. Integral 1 to 2 of the square root, because that is the utility function that we've assumed for the student. Y take away R of Y, dy is bigger than or equal to 0.75. So again, I'm going to base that bigger than or equal to 0.75. We can essentially assume that it equals 0.75. Because it's at least 0.75. So if it's 0.75 or more, then they'll take on the loan. So I'm going to assume that's an equals here, okay? For the purposes of the Lagrangian, I'm going to assume that. So it's subject to this. And what we need to do now with the Lagrangian, so the Lagrangian, it's what we want to maximize or minimize, in this case maximize. So it's all of this. The profit for the student loan company, plus lambda times the constraint function, as I call it. So basically, we want to make this business here with the side constraint 0. So I take away 0.75 from both sides. So I have integral 1 to 2 root y minus r of y dy, take away 0.75. And basically, we want to differentiate with respect to r, set that equal to 0, find lambda, sub lambda back in, the same sort of stuff as before. So So what I'm going to do now is I'm going to do the same trick that I used before, and I'm going to put everything under the same integral sign that I can. So I have integral 1 to 2 of, right, r of y plus lambda times that square root, y minus r of y. Just expanding this, lambda times the first integral, lambda can go inside, dy. That's everything under the integral sign. I have a minus 0.5, which is not under the integral sign. I have lambda times minus 0.75, minus 0.75 lambda. And then I need to do dl by dr. Now, if I differentiate with respect to r, let me just get a new page because I've now run out of pages. There we go, that's fine. I want to do dl by dr, and I need to set that equal to 0 because I want to find the value of r that maximizes, so I differentiate with respect to r. So I do dl by dr. We can use Leibniz's rule to say that I can just take that partial derivative and take it underneath the integral sign. So I have integral 1 to 2 of d by dr of r, I'm just going to call it r from now on, plus lambda root y minus r dy. And then if I differentiate constants, I'm going to get 0. So these both go to 0. Well, they're not 0 there, but they will when I differentiate. We set that equal to 0 for the first order condition. Now, once again, I'm going to make the assumption that because I'm integrating from 1 to 2, so over a positive domain, and the integrand, so this business here, is non-negative, then it actually has to be 0. In order for the integral to end up as 0, the actual function that I'm integrating inside must be 0 because, look, I've got r of y, that's money coming in. Lambda, I presume, is positive. Square root is positive. So basically, what I've got in here is something non-negative. So when I'm integrating it and I'm ending up with 0, it must be that the actual integrand itself is instantaneously 0. So that means d by dr plus lambda root y minus r is all 0. Basically, just say, if I'm integrating and I'm getting 0, the thing that we're integrating, we can say, oh, that is 0. Okay, it's not a general rule, but it's something which we can usually assume. So now let's do the differentiation. D by dr of r is 1. D by dr of lambda root y minus r, well, it's a partial derivative, so that means y is a constant as far as we're concerned. Differentiate well, I'll tell you what I'll do actually. I'll make that into a power of a half. That might make it easy to see. D by dr of r is 1 plus lambda times inner function derivative of minus r is minus 1. Bring the power down, minus 1 from the power. So I get this business. So I end up with, I don't like the fact that shouldn't be a 3, that should be a 1. 1 half take away 1 is minus a half, sorry. So I've got 1 plus, and then lambda times minus 1 is minus lambda. So I have minus lambda times a half minus lambda over 2, y minus r to the minus half. So my aim now is to basically work out what lambda is. But I need to get the side constraint in as well. So I'm just going to rearrange this to make it look a bit nicer. So I'm going to add all of this to both sides. So I have 1 is equal to lambda over 2 y minus r to the minus half. But that just means that I've got times 1 over the square root of y minus r. So what I'm going to do, I'm going to multiply both sides by root y minus r to bring it up to the left. So I have root y minus r is equal to lambda over 2. I'm going to square both sides. Y minus r is equal to lambda squared over 4. I'm going to add r to both sides. So we get y is equal to, or actually I'm going to get r on its own. So r is equal to y minus lambda squared over 4, which I think we had earlier actually, but that's fine. And the aim of the game now is to get lambda. So we need to look at the side constraint. So the side constraint was this here, integral 1 to 2 root y minus r of y was 0.75. So we'll sub that in. So we know r of y in terms of lambda. Yeah, so we can do integral. So we know integral 1 to 2 of root y minus r, but we know this is our expression for r. So take away y minus lambda squared over 4 dy. That's going to be 0. So that's not 0, sorry, it's 0.75. Get a new page. Sorry about this. There you go. Right, so let's simplify that integrand. Integrand is just the thing which I'm integrating. So square root y, take away y, minus 1 times minus lambda squared over 4 is plus lambda squared over 4 dy, and that equals 0.75. I've got integral 1 to 2, y take away y is 0, root lambda squared over 4 dy is equal to 0.75. Doesn't matter that it's dy really. So if I square root lambda squared over 4, that is the same as the square root of lambda squared over the square root of 4, which is basically going to be mod lambda, but we can just think of it as lambda. If I square root something, if I square root a square, it undoes the square. So just lambda over the square root of 4, which is 2. So we really have the integral from 1 to 2 of lambda over 2 dy, which is just going to be, not lambda over 2, which is just going to be lambda over 2y, because I'm just integrating a constant from 1 to 2, which is lambda over 2 times 2, take away lambda over 2 times 1, which is just 1 lot of lambda over 2. And that is 0.75. So we get lambda over 2 is 0.75. So to get lambda on its own, I just basically bring lambda up. I bring 2 up to the right hand side. I multiply both sides by 2. Lambda is 2 times 0.75, which is just 1.5. If you have 0.75 is 3/4, you double it, you get 3 over 2, which is 1.5. So that's lambda. Now the aim of the question is to get the student loan company's optimal debt contract, the contract which will maximize the student loan company's profits, which again is a useful problem tool to do. So we need to plug in lambda, so into our r of y function. R of y was this, it was y minus lambda squared over 4. So I need r is y minus lambda squared over 4. So I'm going to sub lambda as 1.5 in there. So I have y minus 1.5 squared over 4. You get y minus, 1.5 squared, 2.25 over 4, 0.5 something. 9 over 4, 9/16, which is 0.5625. So we have y minus 0.5625. So that is the debt contract function, which will maximize utility, maximize the profits, basically, for the student loan company. Now, this was not. I don't think this was an easy problem, to be honest. I think, for me, I quite like this question, because I think there's not a lot of setup. You just basically got to see, right, for each of the parties involved, the student, the government, and the student loan company, what is the expression for their net income? Bang that into the utility function, you work out the expected value, or you write an expression for the integral to get the expected value. You put it into a Lagrangian, you find lambda, you find the function. So for me, it's quite a nice problem because it's quite the actual steps in that thought process are quite easy, but the maths does get fairly involved. I will give you that. So I'll make another video on. I'm not sure. I haven't got it. I haven't downloaded it, I don't think. But no, I have. I got it here. So I'll make another video on. If it's no, it just crashed. I'm not going to be able to do that. But I'm going to make. I will make another video on another one of the problems. So the point is, if we can guarantee, a couple of the problems, then it won't matter so much if we get this one. But anyway, if there's any problems, do let me know. I'd be happy to help.